Hi everyone, welcome to this episode of Keipert Labs. In this video we're going to be looking at how we can start to make calculations of pressure, volume and temperature. When we're looking at the behaviour of gases and exploring the relationships between these things a little bit better. Okay, so we're going to look at pressure versus volume, pressure versus the number of particles, and pressure versus temperature. Okay, so first of all let's have a little bit of a look at the graph of pressure versus volume. I'll remind ourselves of what that graph looked like. Okay, so we saw this sort of a relationship going on. Okay, remember we talked about it being a hyperbola. We said that we used the phrase inversely proportional to describe that kind of a curve, and mathematically we said that that pressure is proportional to 1 over the volume. And that's kind of mathematically how we can describe that as 1 goes up. You know, if pressure increases, volume decreases. Okay, as volume increases, pressure decreases. We can look at it either way around. Okay, but so what we're going to see is now we can, rather than just describing these qualitatively using arrows, that we can actually describe it mathematically as well. Okay, so what we're going to do here, just a quick little bit of maths, so bear with me here. For those who maths kind of makes you shiver a little. Alright, so what we've just said is that pressure is proportional to 1 over the volume in a given kind of situation. But working with this kind of proportionality kind of symbol expresses a relationship nicely, but we can't really calculate with it because this isn't an equal sign. We want to see if we can turn this into an equal sign. And so what we can say is, alright, pressure equals some constant number divided by volume. Okay, so this number helps us to actually describe or to kind of work out how, kind of how we can translate between these two numbers. Okay, so this is just some number. I've just given it a symbol of K because maybe K for Keipert Labs. Let's go with that. All right, and so what I'm going to say is, all right, well let's say pressure times the volume is equal to this number, this constant number. So whenever I have the sample of a given gas at a given kind of temperature and number of particles, that will stay the same, that the pressure times its volume at that will equal a particular number. So that means that if I've got if I've got one set of pressure and volume conditions, that's equal to this K. If I've got another set of pressure and volume conditions, that's also equal to this K. You know, if I've got a different set of conditions that I've measured, it's also equal to K. You get the idea. It's very kind of straightforward. A lot like as far as we see that we get the same pattern. Sorry, not that it's a straightforward idea, because I realize some of this is a bit weird for you. But so what we can say is, all right, well let's kind of look at this pair here and say that if both of these things are equal to this constant number, so a constant number, then we can actually take the leap and say that those conditions are equal to each other. That is saying that for this gas at this temperature, that any times that I have any pressure and volume that I have multiplied together will be the same as any other. Okay, so it doesn't matter what these numbers are. If once I multiply them together, that they will equal these two numbers multiplied together. Okay, and this is something I really want you to put a box around. Put asterisks in the corner. Highlight it, if you will. Point arrows towards it if it helps. Okay, this is the first relationship we're going to work with here. So if I say, all right, well, I've got a pressure of 100 kilopascals, and I know that it takes up 2 liters at those conditions, and then I say, all right, well, now I want to work out, you know, what's the pressure when the container is made up to 3 liters. What I can do is I can say, all right, well, these two things multiplied together is the same as these two things multiplied together. And so now what I can do is I can solve for x like any other equation that you've ever dealt with. So 100 kilopascals times 2 divided by 3 gives me my answer. And so what I end up with here is I end up with around about 67 kilopascals of pressure. Okay, now and we can always use a little bit of common sense to check on this. As far as we can say, right, well, we started with a higher pressure, we made the container bigger, so as the volume went up, the pressure should go down. But now what we can see is it's going down proportionally, so it's 2/3 of what it was before. Okay? All right, now we're going to have a look at pressure and number of particles. Okay, so what we saw with this relationship was a directly proportional relationship. That is, we're saying that pressure is proportional to the number of particles. Okay, and so just as before, what we can do is to take the proportionality out of this, let's introduce this constant K. Okay, or some constant. So we can say that pressure is equal to some constant number multiplied by the number of particles. Okay, so just as before, we can say that when we have, sorry, back up a bit. So now what I can say is, all right, so that I can take the pressure and divide it by the number of particles and I get some constant. So I can say when I get a certain number of pressure at a certain number of particles, that will equal K, which will also equal the pressure and number of particles at some other, like some other conditions here. So what we can say is we get this relationship going on here. Okay, so this is the second one that I really want you to highlight an asterisk. Okay, so that's saying, all right, so let's say when I have a pressure, I get a pressure of 150 kilopascals when I get 5 puffs of air. Okay, now at the moment we're only talking about puffs of air. In a later unit we're actually going to quantify the number of particles. Okay, so let's say we've got 5 puffs. And then we want to say, all right, well, if I then take this gas and then I remove some air and then I detect it to be a pressure of 60 kilopascals, how many puffs is that? Okay, and so we can then kind of cross multiply. 150x is equal to 60 times 5. Okay, so x is equal to, so 60 times 5 is 300 divided by 150, so we get 2 puffs. Okay, so we can use this relationship. We use this relationship and substitute in to say that, okay, and if I know the pressure and the number of particles in one set of circumstances, I can work them out in another. Okay, now we're going to have a look at pressure and temperature. Okay, so here we're looking at the relationship between pressure and the temperature in Kelvin. Remember in the previous video we introduced this Kelvin scale, and so what we're saying here is that just like our pressure versus number of particles, that we have a proportional relationship. Okay, that as we double the temperature in Kelvin, we double the pressure. As we halve the temperature in Kelvin, we halve the pressure. Okay, so we can say that pressure is proportional to temperature. Okay, so that means that pressure is equal to some constant multiplied by the temperature, as long as we're in Kelvin. You must stick with Kelvin. Always go with Kelvin. Okay, and so, same as before, we can say pressure over temperature is equal to this constant. So any time that we take the pressure and divide it by its temperature in Kelvin, we will get a constant value. So that if we have it at one set of conditions, that will equal K, okay, which will be the same at a second set of conditions. Okay, and so what we see is this relationship here. This is our third one. Okay, that I want you to kind of get used to here. Okay, and so so let's kind of say, all right, so let's say we have a sample that's got a pressure of 100 kilopascals when the temperature is so 273 Kelvin. Okay, so which is basically 0 Celsius, and we want to say is all right, and then we say let's take that up to 25 degrees Celsius, and then we can work out what the pressure is going to be. So here we can now, because we have x as our numerator, we can multiply by 298, okay, over 273K, okay, and so we get around about 109 kilopascals. Okay, which fits now logically with what we're looking at, is that we can say, right, that as we make the particles move faster, that they're going to push harder on the container. They're going to exert a greater pushing force, so the pressure we will experience will be higher. Now, one thing that I just want to quickly draw your attention to here is that we can actually say, all right, well, let's look at this fraction as 100 kilopascals multiplied by this fraction, which this is the ratio of the temperatures, okay, in Kelvin. Okay, so we can use this idea of ratios to then work out what our new relationship would be. Okay, so you don't even necessarily doing a substitution into this equation. You can look at the ratios and say, all right, well, if the temperature doubles here, that then my pressure will double. If my temperature is half, it will be half. If my ratio is 1.5, then it will be 1.5. Okay, so you can actually use that concept of a ratio to perform these sort of calculations. Okay, I would imagine that most of you would be more familiar with a substitution like this. Okay, and so then that can make things a little easier. All right. So what we've got three different proportional or three different relationships that you can use depending on what kind of calculation that you're after. We've looked at the pressure multiplied by the volume, and any particular one set of conditions is equal to the multiplied together in another set of conditions. Okay. We've looked at that the pressure divided by the number of particles in any one set of conditions is the same as in any other. And now we've looked at this idea that the pressure divided by the temperature is equal to the pressure divided by the temperature in another set of conditions. Okay, so that we can choose relationships 1, 2, or 3 depending on what are the variables that are changing. And so we can ask ourselves what variables, gotta love that word in science, are constant. Okay, so in the questions that you're going to be doing calculations for, that some, is it pressure constant? Is the number of particles constant? Are we working with constant volume or temperature? Okay, so some things will be constant, and so therefore, what variables, or maybe we should say which variables are changing? Okay, and so we can kind of work this sort of thing out. Okay, so what that then allows us to do is to be able to perform calculations relating pressure, volumes, and temperatures at two different scenarios, two different settings, accurately and quantifiably. Okay, so there'll be some practice questions to go on with now. Here we go. We're going to finish with Keipert's meme of the day. Thanks for watching. Bye for now.